This particular video episode is going to be about quantum numbers, electrons, sublevels, orbitals, and electron configurations. To begin, we're going to focus on there's 4 quantum numbers that are used to describe an electron's location. The quantum numbers essentially give an address, similar to like a street address for a home, to let us know exactly where we can try to find that particular electron. The first quantum number of the 4 is known as n. What n represents is the energy level for a given electron. For example, in this rather crude picture of an atom, at n equals 1, that's our first energy level. It's the lowest energy level surrounding the nucleus of an atom. If we move up to n equals 2, we're now at a higher energy level where we're going to locate our electrons. This outer layer here would be an even higher energy level known as n equals 3. With successively higher and higher n values, what we can say about electrons is that they're moving to higher and higher energy states. Another way of saying that is they're getting further and further away from the nucleus of the atom. The second quantum number, represented by L, represents an electron's sublevel. A sublevel is something we're probably familiar with or seen before. Something's referred to as the S, P, D, or F sublevels surrounding an atom where we can find electrons. Now the value of L can have a value ranging from n-1 or less are the restricted values for what L can possibly be equal to. For example, at n equals 1, L is n-1 or less. 1 minus 1 equals the value of 0 for our value of L when the energy level is 1. This L value of 0 corresponds to the S sublevel. The S sublevel, we may recall, is just a sphere-shaped sublevel. So when we have an L value of 0, what that's communicating is that the sublevel we're in is the S sublevel or sphere-shaped sublevel. When we go up to n equals 2, the next energy level, now our value for L can be either 0 or 1 because we can be n-1 or less for the value of L at any given energy level. The L equals 0 value will once again correspond to an S sublevel. The difference is now at energy level 2, we're at a higher energy, so the S sublevel is larger and a higher energy than at level 1. The shape, however, is still the sphere shape for the S sublevel. When we move up to L equals 1, L equals 1 corresponds to the P sublevel, the familiar dumbbell or teardrop shaped sublevels that identify a different location for our electrons. Now, as we continue to move up energy levels outside of an atom, what we see is with each successive increase in energy, we see the addition of one additional sublevel as we move through the S, P, D, and finally F sublevels surrounding an atom. For example, when we start out, when we're only at n equals 1, the only sublevel possible is L equals 0, which is the S sublevel. However, as we go to energy level 2, energy level 3, energy level 4, we keep adding in one additional sublevel. For example, once we get to energy level 4, we have L equals 0 for the S sublevel, L equals 1 for the P sublevel, L equals 2 for the D sublevel, and then finally at L equals 3, that identifies the F sublevel for all the different regions where we can find electrons outside of an atom. Next up, we move to the third quantum number, which is known as m sub L. The information provided by the third quantum number, m sub L, is m sub L defines for us the number of orbitals that are within a given sublevel. The possible range and value for m sub L is it extends from positive L to negative L for a given sublevel. For example, when we have L equal to 0, that identifies us as being in the S sublevel. The possible range is positive L to negative L. The only possible value then is 0 for m sub L at L equals 0 or the S sublevel. Now what this single value of 0 tells us with m sub L is that there's only a single orbital then in the S sublevel, which we know to be this single sphere-shaped orbital within the S sublevel. Let's take a look at another sublevel. In this case, when the L value is equal to 2, that identifies our sublevel as being the D sublevel. The possible range again for m sub L ranges from positive L to negative L. So this would give us values of +2, +1, 0, -1, and -2 for our m sub L values when we're within the D sublevel. Because plus L ranges from positive 2 to negative 2, that gives us 5 distinct values for m sub L when we're at an L value of 2 for the D sublevel. What this indicates for us is that within the D sublevel, we have 1, 2, 3, 4, 5 orbitals, with each orbital corresponding to one of the 5 separate and distinct m sub L values that exist when we're at L equals 2. So the m sub L value is what tells us how many orbitals we have within a given sublevel. The fourth and final quantum number is known as m sub S. The m sub S represents the electron spin for an electron. The possible values for m sub S are either +1/2 or -1/2. M sub S just indicates to us that an electron can either be spinning in one direction or the electron can be spinning in the opposite direction. One value is +1/2, the other value -1/2. At this point, pause the video and attend to question number 1 with your lab partner. A few more things to address with our electrons. One thing being, at any energy level, there's at most n squared orbitals possible at a given energy level. The other item being that the maximum capacity for any orbital is 2 electrons at most. 2 electrons per orbital is the maximum capacity. A couple more things is that as electrons fill in around atoms, there's 3 rules that govern how the electrons fill in. The first of these, known as the off-ball principle, affectionately also known as a lazy boy recliner principle, which tells us that if electrons have an option, they're going to enter the orbital of lowest energy first, prior to filling orbitals of higher energy. A second rule is known as the Pauli exclusion principle. Pauli exclusion principle tells us no 2 electrons can have the same set of 4 quantum numbers. Translation on this is that no more than 2 electrons may fit into any single orbital. The third and final rule is known as Hund's rule. Hund's rule tells us that electrons, if we have multiple orbitals, say 5 orbitals in the d sublevel, electrons fill in one at a time before they double up in any of those orbitals. That would be Hund's rule. At this time, take out a blank plain paper periodic table, and we're going to number the periodic table for energy levels and identify the location of the sublevels that we're then going to use when we do electron configurations and molecular orbital diagrams. To start, along the far left edge of your periodic table, number 1, 2, 3 next to hydrogen, lithium, sodium, potassium, and so on down the first column. Above the first 2 columns, label this as the S sublevel territory. The numbers you're putting along the edge represent the energy level. Similarly, mark your periodic table at 2, 3, 4, 5, and 6 as we go down right next to boron, aluminum, and gallium. Right above this section, label this as the P sublevel section of the periodic table. Right next to scandium, yttrium, moving down, label a 3, 4, 5, and 6 right on the boundary, and label this section as the D section of the periodic table. And then lastly, down below here where there's a section chopped out of the periodic table, label this as energy level 4 and energy level 5, and then identify this as being the F block or F section of the periodic table. Let's now use the periodic table to do something known as an electron configuration, which is us identifying the location of all the electrons for a specific atom. Let's start with hydrogen. Hydrogen's here at energy level 1, and it's in the S sublevel. Hydrogen contains 1 electron. Our configuration would look like this: 1s1. The 1 here identifies us as energy level 1. The S is the sublevel that we're in. The superscript is the total number of electrons that are in the 1s sublevel. Let's try another atom such as carbon. Now carbon is right over here in the second row of the periodic table. To get to carbon, as we fill in the 6 electrons in carbon, we pass through the first electron, we have hydrogen, work our way over to helium. So at this point, our configuration would look like this: 1s2. The energy level 1 sublevel S is now full, so we wrap around on the periodic table, come back to energy level 2. As we proceed through lithium and beryllium, at beryllium we're now at energy level 2, sublevel S, and we have 2 electrons. We have 2s2. We work our way across over here. We're at energy level 2. We're now in the P sublevel, and we have 2 electrons as we go to carbon, so it would be 2p with a superscript 2. This would be our electron configuration for a carbon atom. Let's next do the element vanadium, right here, element number 23. As we proceed, starting at hydrogen, we're going to work our way over to helium. At that point, our configuration is 1s2. We wrap around to lithium and beryllium. We're now at the point of 2s2. We work our way from boron across to neon. That brings us to 2p6. Energy level 2 is now full, so we wrap back around to energy level 3. As we go to sodium and magnesium, we're at 3s2. Work our way across, we get to aluminum through argon, and we're at 3p6. We have a little kink now. We work back here to energy level 4, potassium and calcium, brings us to 4s2. But now the pattern is such that when we get to the D sublevel, we're back at energy level 3. So as we go to vanadium, we have 3D. We're 1, 2, 3 columns over, so it would be 3D3. This would be the longhand electron configuration for vanadium. If we wish to do a shorthand electron configuration, what we do is identify the noble gas that comes before vanadium. In this case, that's argon. And we write argon in brackets And then we write all the electron configuration that comes subsequent to the element argon. What this does is identify the outermost or valence electrons of our element. This would be the shorthand form. This below is the longhand form of an electron configuration. The last thing we have is something known as an orbital diagram for our elements. Let's use carbon since we already have an electron configuration that we did for a carbon atom. What an orbital diagram does is identify by sublevel where all the electrons are located. In doing an orbital diagram, we draw a line to represent each orbital. In this case, 1s has a single line for the 1 orbital in the 1s sublevel. We have one line for 2s. And then for 2p, because we have a +1, 0, -1 m sub l values in the p sublevel, we have 3 lines, each line representing a single orbital within the 2p sublevel. Our electron configuration says we have 1s2, that's 2 electrons. The first electron in for an m sub s value of +1/2 is drawn with a half arrowhead up. Then we pair it up, m sub s -1/2 arrowhead down. We go to the 2s sublevel. We have 2s2, so we have m sub s positive, arrowhead up, m sub s negative, arrowhead down. And then 2p2, following Hund's rule, we have one arrowhead up for +1/2 m sub s, and the second electron goes into the next orbital, in that each orbital gets 1 electron before we go back and double up, and that would be following Hund's rule. This would then be what we call an orbital diagram for a carbon atom.